Every year, Japan produces millions of tons of steel, but only a fraction of it becomes the heart of what is considered a modern engineering miracle, the rails for the Shinkansen bullet trains. Imagine a furnace larger than a 5-story building, heated to over 1,500 degrees Celsius, where iron and carbon boil. This ocean of fire is transformed into rails the length of a football pitch, so perfectly straight that the smooth glide of a train at 320 kilometers per hour depends on them. But the real secret lies in how Japanese engineers fuse these rails into a continuous ribbon, up to 1.5 kilometers long. Do you want to know how they created the illusion of an endless rail without a single click-clack? Watch until the end. We are inside a vast Japanese steelworks. The atmosphere is heavy, thick with a mixture of intense heat, the smell of steel, and the deep hum of powerful machinery. Before us stands the main character of this scene, a steel-making furnace the size of a 5-story building. It resembles the mouth of a volcano, glowing a blinding white. Inside, a boiling mixture of iron and carbon churns at over 1,500 degrees Celsius. With a roar, the molten metal is poured into special molds, like a brilliant orange river of lava flowing down a mountainside. Against the scale of these immense machines, the workers look tiny. After the steel is cast, it begins to cool, transforming from a liquid into a solid, yet still intensely hot block of metal. The rolling mill is a colossal machine, something like a giant meat grinder. But instead of blades, it has heavy steel rollers that crush and stretch the metal. The deep rumble intensifies as the machine grips a red-hot billet. With a sound like a low groan, the hot steel begins to elongate, like dough for pasta, but dense and heavy. Gradually, this billet becomes longer and straighter until it finally emerges as a single continuous rail, almost 100 meters long, the length of a football pitch. The surface of such a rail must be absolutely flawless, without the slightest ripple. Because if it is even minutely uneven, a Shinkansen train will not glide smoothly over it. After rolling, the rail is still incredibly hot. Steam rises from it, and you can hear a crackling sound, like water hitting a scorching hot plate. But this is its almost finished form: long, heavy, smooth, ready for inspection, grinding, and its future life. To reduce the number of joints, Japan uses a method of continuous welding, where several rails are fused into one extremely long ribbon. The welding of rails for high-speed trains like the Shinkansen is a high-precision process, with the goal of turning individual sections into a seamless track up to 1.5 kilometers long. It is this type of joint that eliminates the traditional click-clack sound as the train passes over it. The welding process occurs in several stages. The most common method is thermite welding, a reliable and visually spectacular technique. 2 rails are positioned end to end, with a gap of just a few millimeters between them. The surfaces of the future joint are meticulously cleaned of any rust or contaminants. A special mold made of a heat-resistant material is then clamped around the joint. A small crucible above the joint is filled with the thermite mixture, a powder of aluminum and iron oxide. When it is ignited, a chemical reaction occurs, generating a temperature of over 2,500 degrees. The result is molten iron, which flows down and fills the gap between the rails, fusing them at a molecular level. The reaction lasts several minutes, accompanied by a hissing, crackling sound as a brilliant flame erupts above the joint. It looks like a miniature volcanic eruption. After the metal solidifies, which takes about 10 minutes, the mold is removed, and the excess metal is sheared off. The joint is then ground down to a perfectly smooth surface so that the train wheel feels no transition. The finished weld is inspected with laser measurements and ultrasonic sensors which search for any potential micro cracks. In a world where every second counts, Shinkansen engineers discovered the secret to permanence, the slab track. Instead of traditional stone ballast, they created monolithic giants from concrete. These Titan slabs can reach a thickness of 66 centimeters, the height of 2 footballs stacked on top of each other. Japanese masters also invented an ingenious solution: encapsulation units. Imagine a metal cradle that embraces the rail like a mother holds a child. These cradles not only secure the steel tracks, but also isolate them from vibration and electricity. But the most brilliant part of the system is what you cannot see. Between the concrete slabs and the foundation, the Japanese placed resilient layers that act as giant shock absorbers. Transporting the sleepers to the installation site is done in several ways. For short distances, special crane-equipped lorries are used. For longer routes, railway flatbeds. Safety during transport is critical. A single concrete sleeper must be lifted by 4 workers, highlighting their significant weight, roughly 75 kilograms per worker. For mechanized lifting, special grabs and cranes are used. On the construction site, the installation process begins with the preparation of the base. For the slab track, which is predominantly used on the Shinkansen, the sleepers are installed onto precast concrete slabs. Each sleeper is positioned with an accuracy of 6 millimeters, as even the slightest deviation can cause problems at speeds of 320 kilometers per hour. The installation is carried out by specialized crews using precision equipment. First, support points are set every 60 centimeters, the standard interval for high-speed lines. Each sleeper is then fixed to the base with special anchor bolts, 2.5 centimeters in diameter, which are driven 15 centimeters deep into the concrete slab. The process is further complicated by the need to integrate with the power supply and signaling systems. The final stage involves installing vibration insulating pads between the sleepers and the base. These rubber steel elements significantly reduce the transmission of vibrations from the trains to the surrounding structures. After the installation is complete, the entire section is tested by a special inspection train. Despite more than 120,000 trains running on the line annually, the average delay is just 36 seconds. Over half a century, the top speed has increased from 210 to 320 kilometers per hour, and the line now carries 1 million passengers a day. A new line is expected to operate at 500 kilometers per hour, with a projected journey time between Tokyo and Osaka of just 67 minutes. Every year, humanity forges colossal anchor chains capable of withstanding a force of over 1,500 tons, enough to hold back an entire freight train loaded with coal. A single link can weigh more than 500 kilograms and be as thick as a tree trunk. But how is such immense strength born from a simple bar of red-hot steel? What brutal trials must every meter of this steel serpent endure before it is trusted to the depths of the ocean? Stay with us until the end to witness a process of fire, sparks, and true engineering alchemy. It all begins not in the forge, but at a steel mill, where a special alloyed steel is created from ore and scrap. This is no ordinary metal. To produce chains that can handle loads of thousands of tons, you need the highest grade of steel, one capable of resisting not only tension, but also the embrittlement that comes from the extreme cold of Arctic waters. After smelting and chemical analysis, the steel is cast into massive cylindrical billets. These billets, while still hot, are passed through rolling mills that, with incredible force, squeeze and stretch the metal, forming it into long, round steel bars with a diameter that can exceed 200 millimeters. The production hall is a kingdom of fire and metal. The air here is thick with the hum of machinery and the sharp, distinct smell of incandescent steel. It is here that the magic happens, transforming a straight bar into a curved, closed loop. First, the steel bar enters the infernal mouth of an induction furnace. In a matter of minutes, a powerful electromagnetic field heats it to 1200 degrees Celsius, making the metal plastic and malleable. The glowing bar is then immediately fed to a bending press. Hydraulic arms effortlessly bend it into its characteristic U-shape. Now comes the critical moment. While still hot, the U-shaped piece is threaded through the last, already completed link of the growing chain. This is how the links are interconnected. The two ends of the U-shaped piece are then brought together and clamped tightly in the giant copper jaws of a welding machine. The process of flash butt welding begins. An enormous electrical current is passed through the joint. The metal at the point of contact instantly melts, accompanied by a blinding flash and a fountain of sparks. At that exact moment, a hydraulic press with hundreds of tons of force squeezes the molten pans together, fusing them at a molecular level into a single seamless piece. The excess metal, known as flash, is immediately sheared off by special cutters. While the link is still hot from welding, a special stud is fitted into its center. This crosspiece not only gives the link additional rigidity, but, most importantly, prevents it from deforming and tangling during use. After the stud is set, the entire chain, or a section of it, undergoes heat treatment. It is reheated to a precise temperature and then rapidly cooled or quenched in a huge pool of water. This process makes the steel extremely hard, but also brittle. To remove this brittleness, the chain is heated again to a lower temperature and left to cool slowly in the air. This final step is called tempering. Not a single meter of a giant chain leaves the factory without undergoing a series of the most stringent tests. This is the guarantee that it will not fail at a critical moment. First, the entire chain is subjected to a proof load test. It is secured in a special testing machine. a colossal hydraulic bench dozens of meters long. The machine begins to stretch the chain with a force significantly greater than its nominal working load. Inspectors meticulously examine every link for any sign of deformation. But the most dramatic trial is the break test. A test sample of several links is cut from the finished batch. It is placed in the same machine and pulled until it shatters. The deafening crack of rupturing metal is not a sign of failure, but the ultimate confirmation of the entire batch's quality. After the mechanical tests, every single link is inspected with ultrasound to detect any hidden internal flaws. Only after successfully passing all these stages does the chain receive its quality certification. Loaded for transport, it looks like a sleeping steel leviathan ready to begin its silent service in the depths of the ocean. For the highest grade chains, this proof load can exceed 1,000 tons. This means the chain is stretched with a force equivalent to the weight of 3 Boeing 747s. The minimum braking load for such products often exceeds 1,500 tons. Behind every giant link is a world of impressive numbers. A single link of a top-grade anchor chain can be forged from a steel bar over 200 millimeters in diameter. The weight of such a link easily exceeds 500 kilograms, more than a grand piano. However, chains are not measured by the link, but in sections. A standard marine section, or shot, is 27.5 meters long. The complete anchor chain for a supertanker can consist of 12 to 15 of these shots, reaching a total length of over 400 meters. Its total weight can easily exceed 250 tons, comparable to the weight of 2 adult blue whales.